In this video, we're going to look at the polar form of a complex number. This is part 1. In this video, we're just going to define what the polar form of a complex number is, and then in part 2, we'll look at a few examples. So, I've got this plane drawn out here, the complex plane, with the real axis and the imaginary axis. Let's mark a complex number on it. So this is my complex number z, and it's equal to a plus bi. So it's being expressed in the normal form that we're used to. Now we know that means that we have a length a here that we've gone along the real axis, and then a length b up the imaginary axis to get to z. So the length of these two red lines here are a and b. Now let's complete this right angled triangle by putting in this side here, and I'll call it r. And I'm also going to mark this angle here, the angle that the line from the origin to z is making with the positive real axis. I'm going to call that theta. Now let's make some observations. So using trigonometry, we can find a and b in terms of r and theta. So I'm not going to go over the trigonometry here. There is a whole set of videos in this series of videos on trigonometry. So if you're not confident with your trigonometry, you should go and watch those. I'm just going to assume you've seen those, or you know how to use trig to find sides and angles in a right angled triangle. So I'll just say that a is equal to r cos theta. If you don't believe me, you can do it yourself using SOHCAHTOA, and you should find that a is equal to r cos theta. Okay, a is adjacent to theta, r is the hypotenuse. So cos of theta equals the adjacent over the hypotenuse. You rearrange and you get a equals r cos theta. Likewise, b equals r sine theta. Do it in the same way. So we have a and b now in terms of this length r and this angle theta. If we plug those into the equation for z, so we change a and b for these things, we'll get that z equals r cos theta, because that's a, plus I times r sine theta, because that's b. And now there's an r in both of these terms, so we factor the r out, and we get z equals r times cos theta plus I sine theta. Okay, so I'll mark this on my diagram that I can say z is equal to r cos theta plus I sine theta. Now this form of z, so it's still just going to give me a complex number. If I knew theta and I knew r and I plugged them in, I would end up with something in the form a plus bi. But when it's written in this form, with the cos and the sine and the theta and the r, it's called the polar form of z. So that's what the polar form is. It's when we write z in terms of an angle and a length from the origin to wherever z is in the plane. So let's just make some observations about these things r and theta. So r is called the modulus of z. So whenever someone talks about the modulus of z, that's what they mean. They mean r, and it is the distance from the origin to z. So we can see that on the diagram. Doesn't matter where z is, the distance from origin to z, so the length of this line I've got on the diagram, the hypotenuse of the triangle, that's r. It's called the modulus. And r is equal to the square root of a squared plus b squared. So that's just using Pythagoras' theorem. A squared plus b squared equals c squared for a right angled triangle. So a squared plus b squared would equal r squared. We take the square root and we get r equals the square root of a squared plus b squared. So if you have a complex number in the standard form, or what's sometimes called the Cartesian form, a plus bi, then you can find its modulus quite easily using a and b. Okay, so what about theta? What can we say about that? Well, theta is called the principal argument of z, and it is the angle measured anti-clockwise from the real axis to the line from the origin to z. So this line that has length r, if I measure from the positive side of the real axis to that line, that is theta. Now you might say, why is it called the principal argument of z? Well, we'll look at that in a moment, but we'll first just look at one more example of a complex number in a different part of the plane, just to make sure we accept that theta is well defined and makes sense. So let's look at z down here now. So say we had z equal to a plus bi, but it was down in this part of the plane. Well, now we can say that this triangle here has side lengths mod A and mod B, are the absolute value of A, the absolute value of B. We have to take the absolute value because both A and B are negative. So it doesn't make sense to say the sides of this triangle are negative in length. So we have to take the absolute value of A and the absolute value of B to get positive numbers. Okay, they're both negative because we've gone down the negative direction from the origin, down the real axis, and then down the imaginary axis in the negative direction as well. So this is what we can say now. And let's say this is still R, our length of the line from the origin to Z. And we'll call this angle theta prime. So why am I calling this angle theta prime? Well, if the angle theta that we use, the principal argument, is measured from the positive real axis to the line here with length R, then that would be this angle. So theta is actually this whole angle here. We go from the real axis, the positive side, around until we get to this line going to Z from the origin. So that's theta. But we can't really use trigonometry to find theta. So what we'd have to do is use the trigonometry to find theta prime, which we can do because that's inside this right angle triangle. And then we note that theta prime is just theta plus pi, right? Because if you go from the positive real axis halfway round till you get to the negative part of the real axis, then that's 180 degrees, or pi, because we always use radians for the arguments of complex numbers. Whenever we're doing things like this in complex plane, always use radians. So halfway around would be 180 degrees, or pi radians, and then we have to add on this theta prime, and in that will give us theta, the whole angle. And then we can say that R is equal to cos theta plus I sine theta. And just convince yourself that this makes sense. You might look at it and say, no, hang on a minute, isn't R equal to cos of theta prime plus I times sine of theta prime? But again, if you do the trigonometry to try and find the side lengths of this triangle in terms of theta prime and R, what you will get is that the one side length, so the absolute value of A, is equal to R times cos theta prime, and the absolute value of B is equal to R times sine theta prime. So Z is not equal to R times cos theta prime plus I times R sine theta prime, because these things are going to give you positive numbers. You can see from the diagram, hopefully, that R cos theta prime and R sine theta prime give you positive numbers. They must do, because they give you the lengths of this triangle. They give you absolute value of A and absolute value of B, but we want negative numbers. We want to get A and B, and A and B are both negative. Well, if we add pi to theta prime, then we will get the negatives of what we got if we just did cos and sine of theta prime. Because if you shift by pi, if you take cos of a number and then you shift that number by pi, you get the negative of the answer, and the same for sine. If you don't believe me, just look at the graphs for cos and sine. You'll see that if you shift along the x-axis by pi, you'll always get the negative of what you had wherever you started. So this actually does make sense. If we take cos and sine of theta, where theta is this angle theta prime plus pi, then we'll get, when we times them by r, we'll get negative numbers. So we'll get the negative of this length mod A, so we'll get A, and we'll get the negative of this length mod B, or the absolute value of B, which is B. So that's what we want. So this always works. As long as you measure theta from the positive real axis round to this line, then you can always write that Z is equal to R cos theta plus I sine theta. So don't get too bogged down in that. Just remember that you always have to find theta by measuring round from the positive real axis all the way around to this line. And don't use the angle that I have here, theta prime. Use the whole angle measured from the positive real axis. So hopefully that makes sense. Now, just one final comment on why do we call it the principal argument of Z? Well, if we look at the definition in the top of this box of the polar form, Z equals R cos theta plus I sine theta, well, I could add any multiple of 2 pi to theta, and I would still get the same thing. If I add 2 pi to a number and take cos of it, it's the same as if I take cos of the original thing. Same for sine, because they have period 2 pi. So if you shift along by 2 pi, you get back to the same place. And that's true of any multiple of 2 pi. So I could take 4 pi, 6 pi, 8 pi, or minus 2 pi, minus 4 pi. Add these on to theta, and I would get the same thing. So any complex number actually has an infinite number of arguments. There are an infinite sort of values we could put in for theta, and we get the same z coming out. So we call theta the principal argument because it's the argument between 0 and 2 pi that is actually equal to this angle. All the other ones are just that original theta plus or minus multiples of 2 pi. So we define this specific theta that's between 0 and 2 pi to be the principal argument. So often when you're asked to find the polar form of a complex number, you're asked to find its modulus and its principal argument. Now, by this construction, the principal argument would be between 0 and 2 pi because it's just this angle measured in radians, so it's going to be somewhere between 0 and 2 pi. Some people, though, like to take the principal argument to be between minus pi and pi. Some people prefer it this way, and you should be told which one you're using. So hopefully on the course you're doing or in the question you're given, it'll say what range they want you to use for the principal argument. If it's minus pi to pi, you can still find it the way I've laid out in this video by finding this angle theta, which will be between 0 and 2 pi. And if the answer you have isn't in the range minus pi to pi, if it's between pi and 2 pi, just subtract 2 pi from it and you'll get an answer that's between minus pi and 0. So if it is between 0 and pi, the answer you've got, then that's fine, you've got the right answer. If it's not in this range, minus pi to pi, and you're told to give it in this range, just subtract 2 pi and you'll get the correct range. So hopefully that all makes sense. And so this is how, given a number, a complex number in the form a plus bi, you can write it in its polar form, r cos theta plus I sine theta.
There was such music in it as she had never heard.